merged, so I'm gonna let that happen. This is good. I liked it. So now we're going to talk about Bayes' theorem, which is very much related to conditional probability. And this one gets really practical for engineering problems because it considers the fact, or it considers probabilities related to testing outcomes for events. Like, for instance, are there defective parts? What are the probabilities that there is a defective part given some rate of defective parts, and etc. So they're actually really practical, and it's a little bit unintuitive sometimes. I don't think it has to be, but it can be unintuitive for folks, so I want to talk about it. So given two mutually exclusive and exhaustive events A and B, what does that mean? What does it mean that they're exclusive? So that means that yeah, there are no, so exclusive and exhaustive means that there are no other possibilities besides A and B occurring. Okay, so no C. And Bayes' theorem, aka Bayes' rule, states that the probability of A given that B occurs is equal to the probability of B given that A occurs times this ratio of probability of A and probability of B. That's not the form we usually use it in, though. Another form that we use it in more often is that the probability of A given that B occurs is equal to the probability of B given that A occurs times the probability of A. So the numerator stays the same, and the denominator we can rewrite as being the probability of B given that A occurs times the probability of A plus the probability of B given that the complement of A occurs, which is not A occurring, right? Times the probability of not A, of the complement of A. Oh man, I covered up my bars. All right. A third way of writing it, which is sometimes used, is 1 over 1 plus the probability, so this ratio, the probability of B given that not A divided by the probability of B given that A times the ratio probability of not A divided by the probability of A. So those are our possibilities. This is a useful theorem for determining a test's effectiveness. If a test is performed to determine whether an event has occurred, we might ask questions like, if a test indicates that the event has occurred, what is the probability it has actually occurred? So this comes up a lot in manufacturing environment, like, so you test certain number of parts, you know a certain number of those parts are defective. What is the probability that, given that you have a defective part, given that your test indicates a defective part, that it's actually a defective part. It also comes into play when you have medical diagnostic tests, and it's really weird when you start talking like that. But we'll consider that when we look at the graph, which I think helps. So the test can either be positive or negative, and this result can be either true or false. So pink is positive, blue is negative. So I'm trying to help us with the color scheme here. And then true is smiley face and false is sad face, because we don't really care if it's positive or negative. We just want it to be true, right? That's like for any good test is going to be true whether or not the result's positive. Like, so if you're testing for something that's defective, you want to know if it's defective or not. So positive or negative, meaning yes, it's defective or not defective. You want to know the truth regardless of what that result is. You don't want to be wrong. So there are 4 options then. Consider an event A and an event that is a test result B indicating that event A has occurred. So the 4 possibilities are shown in table 4.1. So there are 2 possibilities in terms of the test. The test can either indicate that the event has occurred, so that would be a positive result, or a negative result would be that the event did not occur. That would be the test result. Then there's also, the possibility that the event actually occurred, and the possibility the event didn't actually occur. So A, it occurred. A complement, it did not occur. All right, so those are the possibilities. So if you have A actually occurring, so the event actually occurs, and you have a positive test result, that means you have a true positive. That's what we call a true positive. That means it actually happened, and our test indicated that it actually happened. That's good. That's good. Okay? So this is like tests usually are for bad stuff. So I'm trying to think of tests.
You were pregnant, you wanted to be pregnant.
Oh, good one. Good one. I like it. I like it. You want to be pregnant. You get a positive, you want to be pregnant, you actually are pregnant, you get a positive test result that you are pregnant, you have a true positive, smiley face. Okay? So maybe let's say that you didn't want to be pregnant, and you were like, the negative came up, and also it would be good that that was actually the case, that it was negative. That is a true negative. But you're actually happy in any case in the sense that you want the test to be correct, right? Even if you don't.
You don't want to get lied to during the test.
Also that.
Right.
With breast cancer screenings, they're finding that the more often you get breast cancer screenings, the more likely you are to get a false positive.
Yeah. So false positives are a real problem with medical diagnostics, as we'll talk about. And a lot of it depends on the probability that you actually have it, just based on so for really rare things, a test is really hard because you're going to get false positives on any test, and if it's a very, very rare disease, the probability that you have it is so small that the probability, even if you have a really good test, probability that you actually have a really rare disease if your test comes back positive tends to be a lot smaller than you think. So that's why they try to have another independent test that will verify it before they decide what to do, because one test is not usually enough. Not every doctor knows that, though. So it's good to know. It's good for you to know this, but it's also good if you're designing defective part tests or anything like that. You want to know if you're measuring something. You want to know, if you have a test for it, you want to know how effective that test is. So the 2 bad possibilities is that you have anything that's false. A false positive, meaning that it says that the event occurred, but the event didn't actually occur. or a false negative, which says that you're not pregnant, but you actually are. So, I think that pregnancy tests use pink for positive too. So, it wasn't a total accident that I used this because,
It's just 2 lines.
but I think the color matters on some of them. I'm not saying that everyone is like that, but I'm just saying there may be some.
No, some of them have like the smiley face on it too.
Probably.
The
The smiley and the frowny in ours, just to clarify though, just mean that it's correct. So the test wouldn't know that about itself.
I'm false. Don't trust me.
You're pregnant, but I'm frowning. Yeah. There's a good sound bite right there. Okay. So that one senator probably said that, right? One recent senator.
Oh.
Yeah. Ooh. Yeah. Bad news. That was bad news.
You're pregnant without frowning.
He had a mistress who got pregnant, and he tried to get her to have an abortion, but he was like a really publicly anti-abortion guy. Yeah. Oof. Oof. Yeah. Anyways, somebody had a bad day. Okay. So clearly the desirable result for any test is that it is true, right? However, no test is true 100% of the time. So sometimes it is desirable to err on the side of the false positive, as in the case of a medical diagnostic. So you would rather say you have something and be wrong about it than to miss somebody having something, right? I mean, so like say it's like a cancer screening thing. Like you would rather tell the person that they have cancer and have them not actually have cancer than to say you don't have cancer and have them actually have cancer.
That is an emotional roller coaster.
It is, but it's like of the two,
Right, but if you
the
send
one's
somebody
better.
off saying you don't have cancer and they really have cancer, they're not trying to get treated for cancer.
Yeah, but it's equally as lame when you don't have cancer and you get told you have cancer, so now you have to go through emotional trauma, then all the fake treatments that you're getting. It's like,
But you
oh, wait,
didn't die from
cancer.
Like, think about how much more you'll live once you're like, oh no, wait, I was wrong.
You don't have cancer. Yes.
I remember, dude, I'll go skydiving that. I'd be like, this is the day. I'm getting good news. Lotto tickets, Vegas. That's what I'm talking about.
All right. So, other times it is more desirable to err on the side of a false negative, as in the case of of testing for defects in manufacturing, say, balloons. When a false negative isn't a big deal, you just don't want to, like, for instance, like shut down the manufacturing line for like having defective ones coming out when they're actually not defective. You don't want a bunch of false negatives in that kind of environment where like having a mess up in there isn't a big deal. So you err on the side of having a false positive rather than having a false negative. So if somebody gets their balloon and it's defective, it's probably not going to be a big deal. Like they probably won't bring the balloons back to the store.
That guy in Up would have died.
The guy in Up would have probably disliked it.
I waited 3 weeks to buy these balloons. They were defective. It's like crying in the store. They're just like, okay, so
Dude, I realize that's actually happened.
oh, here we go.
I don't even like being around retail like as a customer. I like to stay away completely.
I'm so sorry.
But speaking of figure 4.
Yeah, so let's talk. Some interesting results can be found from this. For instance, we can plot, as in figure 4.1, the relationship between the probability of a positive test result given that an event actually occurs, so that would be probability of B given that A, and the probability of the event occurring given that the test is positive, probability of A given that B. Okay? Now, in some cases, it is the conditional probability of a true positive given, in both cases, it is the conditional probability of a true positive given some condition. So, but this is the most interesting, or you can plot the other one, but this is usually the one that's most interesting. So, starting out with, if there's zero probability that event A occurred, then the probability of event A occurring given that event B occurred, still zero. You can't rise up out of it. You're still just bam down there at zero, flat line. It can't occur, so it can't occur even if B occurs. It's, what you would expect. And then it has this relationship as you increase the probability of A occurring that also depends on the probability of B given that A. Okay, so a lot of times we think about the probability of B given that A as like the effectiveness of your test. Like, say you have a test that if you have cancer, it returns, 80% of the time it indicates that you have cancer. Not a great test, I would argue, but that would put you like right here on this curve, right? 80%. So so if you have an indication that you have cancer, say, let's say the probability of you getting cancer is like 0.01, so it's like 1%. I don't know. It's probably more like 5, I think, maybe 20. What is it? Do you guys know? It's somewhere in here.
It's pretty high.
We're gonna go with 5 because that makes me feel better. Okay. So let's say it's 5% chance. Then that's actually this line right here. So if you have a test that's 80% effective, you could say, then if you come back with a positive result from that test, there is a 18% chance you actually have it. Yeah.
You have a 50% chance you're going to get cancer.
That's what I would say.
You're being really optimistic with that 5%.
You're off by 10.
Wait, what?
50%.
Do you have a 50% chance of getting cancer?
Getting some kind of, it doesn't say it's like major cancer.
Jeez.
It just says of getting cancer.
Keep in mind, that could be the
radiation.
I'm running out of reasons not to start smoking.
One or more of yourselves is going to give up on its job, and we'll talk as buddies.
Jeez. Ouch.
Look, let's not operate those highways. Let's be rebels.
Let's say it's like some more rare disease that I feel more comfortable about. So, like, even if you have an 80% like effective test, if you have a positive result, there's still only like an 18% chance you actually have it. Some diseases are much more rare than 5%, though. Like, there are some extremely rare diseases, and you can see that. I went down to 1%, but then like I started to run into issues with my the solver was having silly numerical precision errors. But this curve goes way out here. So you have to end up with a really, really highly effective test in order to have any confidence that a rare occurrence is properly detected. And for really rare diseases or for really rare defects in like a manufacturing process, it makes it really hard to test for them because the probability that the thing actually happened is really low. So having an effective test is hard. So let's this example will take just a couple minutes. So I'll just finish it. Yeah.
The part where it says part A on 1 at the very top, is that just like if you do have A, you're guaranteed to get it?
Oh yeah. So this one. So if you go all the way up here, then if the probability that A occurs, like for instance, if there's a 100% probability if everyone gets cancer, then it doesn't matter what your test result is. You have cancer. Like that's the interpretation there. Yeah. It is. I don't know. I feel like it's for some reason it's like the best way to talk about this is like
If
like
everyone
bad
wrote a
disease
sentence,
test. I mean, you could talk about it like this is we're gonna do an example with springs and like defective springs, and nobody's gonna remember that. Everybody's gonna remember the cancer thing. So, I don't know what to tell you. So suppose that 0.1% of springs manufactured at a given plant are defective. Suppose you need to design a test that has probability of 99% that a part, given that it is indicated defective, is actually defective. What probability should your test have, given that a part is defective, of indicating that it is actually so? So what I'm asking you to do is to figure out where you should be on this horizontal axis such that you have a 99% chance of detecting it properly. So, so if you detect it, if you have a positive test result, that it's actually defective. So we'll say event A is spring defective. And we'll say that B is spring indicated defective. So we know that the probability of A occurring is 0.1%, right? So 0.001. And the probability of A, so probability that it's defective, given that B, that the test says it's defective, we say we want to design it so that it's 99%, so 0.99. We need to compute the probability, of, given that the event that the spring is defective, that we indicate it as such, required such that we get this probability of A given that B. So that's our job here. And so probability, so our formula is probability of A given that B is equal to long fraction probability of B given that A times the probability of A, which is just from our formula, divided by the probability of B given that A times the probability of A, plus, and then we're going to do a little bit different here. The formula says probability of B given that not A. That is just 1 minus the probability of B given that A, right? And the probability of and then the next one is probability of not A, which is just 1 minus the probability of A. And then I'm not going to go through the steps, but you can solve that for what the probability of B is given that A. It's the only unknown in this equation, but it shows up thrice. Yeah, you like that? Probability of A given that B, 1 minus the probability of A, divided by the probability of A, plus the probability of A given that B. Holy notation, right? 1 minus 2 times the probability of A. Okay, so we know all of these things, so we can plug it in, and what we get is 99.999%. Which is like, we gotta be, so in other words, we have to design a really, really, really good test.
The test is the spring is broken in half.
Yeah, it's when you start talking about that many nines, it's tough to design a test that's that accurate. But recognizing that if you want these sorts of goals, that you have to have really good tests is really, like, I think the most important takeaway. Being able to use this is also important. If you guys want to supplement this lecture with a really fun thing, look up the Monty Hall problem. Okay? The Monty Hall problem. So it's a really fun thing. There was an actual game show where Monty Hall was like the host. I don't even know. It's like 3 doors.
Didn't we have this discussion?
Did we talk about this?
Yeah.
I know I talked with somebody about this recently.
What is the probability that this has happened already?
I would have to Google it, so I feel like you guys are just as good at that as I am. But anyways, Monty Hall. Pretty cool problem. The goats.
Always from the humans to the other.
Yeah.
Always change your answer.
Change your answer. But it's depend on Bayes' theorem. That's the idea.
Yeah.
Okay. It's because you're choosing from a smaller sample space now. So you're in the second choice, you restricted your domain down to a smaller domain, which is why your probability goes up when you change your answer. But anyways, it's a fun one. But it's all the same. It's conditional probability and Bayes' theorem. So it's good stuff.